So this is a feature selection tutorial. So we start from the very, very basic, okay? We start from very, very basic. So this tutorial consists of 1, 2, 3, 4, 5, 6 parts. So roughly half an hour apart. Then you will have 3 hours. Yes? Okay, but you will also have your coffee break. I remember that, coffee break. So the first one is about the introduction. And why? What is introduction and why? Why? What is feature selection and why do we need feature selection? I need to get my water. Okay, if you come here, very likely you already face the problem with high dimensional data. Okay, we just show you some examples here, but it's not exhaustive. Okay, so these are the. If you think we have more than these 5 types, very likely. Okay, so the key is we have more data, and we have a lot of high dimensional data. Okay. This is like a documents and text, but this is actually tag clouds, and just show you something related to the text. We have these image, all kinds of image data. Then this is really high dimensional data with, well, usually it's a fat data, okay? You have very few instances, but a lot of the genes, right? Number of genes can be like 40,000. So we have time series and the videos. And you will see a lot more about images and videos in the future. Now, problems with high dimensional data. There's something called the curse of dimensionality. How many of you have heard about curse of dimensionality? Excellent. That explains why you are here. So you still believe that feature selection is needed. Huh? So we will give you some example. Maybe you haven't heard about the curse of dimensionality. We will give you some example later, okay? Very quickly. So the key here is when we have high dimensional data, for a particular application we have, probably the intrinsic dimensionality of the data could be small. And could be, if you talk to biologists, they work on the wet labs, they are interested in only 1 or 2 or 3 or something. So if you can help them to focus on few, they will thank you tremendously, okay? Because for one gene, they can produce a PhD thesis. All right, curse of dimensionality. It's about one consequence of curse of dimensionality is about overfitting. But what is that? So let's say we have number of features, D assume it's large. Then the model can be overfitting the data, overfit the data. And if we have n samples, and so now we have D dimensionality, n number of features. So if D is very large, we don't have enough data, then there's a potential for you to overfit. So you said overfitting. So what? Give you an example, just here. So for instance, to estimate the covariance matrix, we need like D square parameters. But if n is very small, is not even greater than D square, then on average, we only have 1 sample per parameter to estimate, right? So it's not very good. But what is the negative effect? So in this case, I hope it's not too small for you. This one called underfitting, okay? Because you have the data points distributed like this, you just have a linear line to fit. So it's underfitting. But then this is overfitting. You see, you can actually describe the data very well if you use a very complex curve. But the problem is when you try to deal with something unknown, then you won't do well, okay? Later on, we will also tell you how can you estimate that, okay? How can you know, like in the new situation, it won't do well? But the ideal case here is just the right case, okay? So if it's like this, then you find the curve, it's not too complex, not too simple, then it will do well. It will do well not just for the training data you have, but it will also do well for the data you haven't seen. This is the key, right? We want to deal with those data points we haven't seen. Now, curse of dimensionality. We give you an example. So data sparsity can become exponentially worse as feature dimension increases. If you just want to remember what is curse of dimensionality, this is a simple understanding. So if we use conventional distance metrics, this is the case. Look at, this is one dimension. I only have one dimension, 1D. Okay, D is equal to 1. Then I have nine points because I have 1, 2, 3, let's say 3 regions, then 3 data points for each region. Now I increase the dimension from 1 to 2. So now it becomes this. Now each dimension has 3 regions. Then suddenly I have 9 units, right? 9 squares in this case. So 9 points, data points for 9 regions. So look, each region has 3. Each region has 1 on average. Then if I increase it to 3D, then I have 27, right? I have 27 these cubic unit. Then each region does not even have 1 data point. So because this is like from 3 to 9 to 27, see, then in terms of the data points, it decreases exponentially, right? The number of units we have increases exponentially, but if we interpret in the other way, then the number of data points we have substantially reduced. So we have a problem. We will have a problem to figure out what is the real pattern we would like to data mine. Okay, so now we have this question. How many data samples do we really need? Okay, there's a very famous theory called in machine learning called the pack learning theory. It's pack learning. So it says basically when we try to learn something, we call it in machine learning, we call it a hypothesis, H. But we really want the target function f. We make h as close as possible to f. But we really don't know about f. If we know about f, then I don't need to learn, right? But if I don't know about f, then how can I estimate? That's the key. So pack learning is very, very useful in theory aspect. So what does it say basically? Pack learning, P is probably, and A is approximately. So C is correct. Probably, approximately correct, okay? So the idea is this, when we don't know about f, the function, real function, and we want to estimate how many data points I can have so I can guarantee the pack learning result. probably, approximately correct. So X is the data samples. N instances, D is number of features. H is the set of possible hypotheses. And hypothesis H is called approximately correct if we say the error of H is smaller than a small constant epsilon. You can specify this, okay? So for a bad hypothesis, then the error of bad hypothesis will be greater than or equal to this epsilon. So the key here is you have F, but we don't know where it is, but we just say, hey, I specify epsilon. Okay, I would like to accept this kind of result. So it's not too bad. If the epsilon you can set it very large, then basically it can cover the whole space, okay? But then, so this is called approximately correct. And the probability that it agrees with the given sample is at most 1 minus epsilon. So I have, remember, we have n samples, right? We have n samples. So for each one, it is 1 minus epsilon. Then we also have this IID assumption. So I can use this. So for each instance, I just consider them independently, okay? So this probability of bad hypothesis agrees with the n samples. If there's a bad hypothesis, it agrees with this. So the probability should be less than this, okay? Then how many data samples do we need? We still need to answer this. The probability contains at least one consistent hypothesis. Is you can calculate like this, okay? So this one is what we said before, right? This is the total, all the bad hypotheses. But then it will be smaller than this one. This is the basically number of bad hypotheses. And previously we just said one bad hypothesis. This is all the bad hypotheses, these. Then together, because they can overlap, that's why this is definitely less than. But H bad, that bad hypothesis space is definitely smaller than the total hypothesis space, right? This is correct. Then we can reduce the probability of this event to below something called another small number, it's delta. Okay? So this, basically this number, this term, at the end, we say it should be smaller than delta. Then we can rearrange this to estimate n. But the key here is, you see, epsilon is a constant, delta is a constant. Basically, how much approximately correct you can accept, that's epsilon. And yeah, right, then probably correct, then this is the delta. But because these are two constants, so we only focus on this, right? Because H is something, is not a constant. So if we just consider a binary data set, okay? Binary data set. If I have D features, it will be 2 to the power of D. But then, of course, we try to learn something. We still use supervised learning as an example. And let's say the class label also is binary. Then the hypothesis space is this many. Okay? It's this many. And then you take a log, then it becomes 2 to the power of D. So this is the interesting part. If we reduce D, it's also the power of feature selection. If we reduce D, we can make data bigger. Okay? We can make data bigger. And this is the example. If I have 5 instances, n is 5 samples, data samples, and I have 10 columns. D is 10. And assuming that there are only 3 relevant features, then what do we have here? You see, this is the space you can have. So the total number of, like, how many data points, total number of data points you can have. That's 2 to the power of 10 for binary data, okay? And then 5, because I only have 5 instances, 5 over 10, 2 to the power of 10 is very small, right? But if we do feature selection, then we reduce the 10 to 3, then suddenly, look, how much data I have. I have more than 50%. That's why feature selection can help you, okay? Feature selection can help you. Now, somebody else also did some kind of study, empirical study, to show that for classification tasks, usually for most of the data sets, you can see this kind of a curve, okay? If you have too few features, the performance does not do well. If you have too many features, the performance also is not good. And then we have some kind of optimal point where the number of features just right for your data mining task. But then you say, hey, we already solved the problem. But the challenge is, where is that optimal point? So feature selection can help you to get close to this point, okay? So we cannot guarantee you we will get to that exact point, but the feature selection can help you. So if you usually, people also talk about dimensionality reduction. So if you just want to reduce dimensionality, there could be 2 approaches. One is feature extraction. The other is feature selection. So we will show you like how different they are. So that for both approaches share the same goal. We want to have this many, you can imagine a lot, of number of features. And at the end, we want to only deal with this many, okay? So the motivation I already give to you. After you reduce, you can have a lot of, you can make data bigger, okay? And feature extraction. There are many methods. You only need to remember this point. Feature extraction basically projects the original high dimension data into a new feature space. So it's from one space to another space. But how do you get that space? That space is given, the new feature space is usually a linear or nonlinear combinations of the previous feature space. You see, these 2 spaces are different now. Okay? This is the essence of feature extraction. But so the new features often do not have physical meanings, not very straightforward. So because they are different feature spaces. For feature selection, we still reduce dimensionality, but the before and after feature selection, the 2 spaces are of the same, okay? So this is the key difference. So now we want to work on relevant, redundant, irrelevant features. If there are no irrelevant features or no redundant features, then we don't need to do feature selection. Every feature is relevant, right? Here, we have F1 is relevant. Then if given F1, then if we add another feature, it's called feature 2. Then in this case, you see, we only need one feature, either F1 or F2. We don't need both, all right? Because the other feature does not introduce anything that the feature, let's say F1, cannot solve, okay? So then for irrelevant features, we have F3. So basically F3 here, it's too small for you, but F3 here, it's irrelevant. It does not help your task, okay? So this is a relevant feature, redundant feature, and an irrelevant feature. It is because we have a lot of irrelevant and redundant features. Usually we have a lot. That's why feature selection helps. So now, the commonalities. So now I'm sure you're convinced now, right? You can speed up the learning process, reduce the storage requirement. But after you map for feature extraction even, improve the learning performance. And if you don't overfit, or you will be able to have generalized model. So differences are, so different spaces for feature extraction, right? So then for feature selection, maintains the physical meaning and give models with better readability and interpretability. Because for domain experts, at the end of the day, you still need to talk to domain experts, right? They will tell you how wonderful you are for your data mining results. So very, very important to many cases very important to maintain the interpretability. Now, we anticipated some of you would attend the deep learning tutorial, okay? And also, how many of you haven't heard about the deep learning? Nobody raised your hand, okay? Very good, huh? So it seems like deep learning can solve everything, okay? Because we have been doing feature selection for some time. So when someone would always ask us when they see us and say, now, do you still need feature selection? Like, I have deep learning. What do you think? Everything is solved. Okay, tomorrow I'm going to give a keynote at a workshop called a Big Mind. The title is Big Data plus Deep Learning equals a universal solution. Question mark, okay? There's a question mark. All right, so of course, I haven't told you, obviously here, right, we still need feature selection, but I need to tell you why, okay? Or you are already convinced? Not yet, right? So many people are working on deep learning. You only hear all the good news you hear, right? Have you heard about the bad news about deep learning? It's so quiet, okay? Nobody will tell you bad news. All right, so deep learning. Oh, sorry, when I was a student, that was in 1988. I took the neural network course that time because backpropagation was so hot. PDP books. How many of you read the PDP books? None of you, huh? Okay, so how archaic I am, you can tell. All right, so backpropagation is wonderful, okay? Because you can go from only linearly separable, that's called the perceptron. Then you suddenly, because of backpropagation, you can solve XOR problem, okay? If you want to know XOR problem, talk to me later, okay? And now you can learn like hundreds of layers of neural networks, okay? But it's great, okay? It's great. But remember, deep learning is one of the machine learning approaches, okay? Just one of them. And Andrew and he just started this deep learning.ai. I think probably a lot of you have heard about this, and they produce this MOOCs course in Coursera, right, for deep learning. Okay, so many people are offering these courses. There's a lot of resources. There are a lot of resources for you to learn about deep learning. But this is what I want you to hear. It is the analogy to deep learning is that the rocket engine is the deep learning models. The rocket engine, we have an engine, then the fuel is the huge amount of data. You see, the huge amount of data we can feed to these algorithms. So we have an engine. Like we have computing powers, a lot of power. NVIDIA, you see their stock market value increases a lot because of a deep learning movement. Okay, so I think I also added another figure here. I didn't see it, and our Jundong Li ignored my change. Okay, I did some change. Okay, it is, still remember the curve? The curve, right? So you have to, if you have too few features, and then you don't do well. If you have too many features, you don't do well, okay? So appropriate number of features, you will do very well. When you have lots of data, yes, you can do very well. But if you don't, when the dimensionality is huge, that means you will demand exponentially many more data, okay? So in that time, we will have a problem, not just for deep learning, for any learning methods, okay? So this is the interpretability of learning algorithms. I noticed some people are trying to take photos of the, I hope you just take a photo of me, not the slide, because we give you the slides, okay, online, all right? So anyway, for your convenience, we provide the slides online. And this is about interpretability. You see, it's not our work. I think we give the credit here. So usually deep learning, the explainability is here. So if you see decision tree, do you still use decision tree, some of you? You still use, you are very brave. So usually nowadays people say, no, I don't use anything else but deep learning. You're very brave, very good. 10 years later, you will be so proud of you, okay? All right, with feature selection, both accuracy and interpretability of most learning algorithms can be enhanced. So there's no exception for deep learning. Summary. Feature selection is simple. I also add another word. It's called the simple, intuitive, and interpretable. And also especially needed when we face high-dimensional data or when we have limited data. It is surprisingly, for feature selection, if you haven't used the feature selection, if you are working on data mining, give it a try. You will be surprised, okay? Don't try fancy stuff, just try simple ones. You will be surprised how effective it is. So later on, now the next part of the this tutorial, we will talk about what is feature selection, what should I know about it, and how can I start. We will tell you these. By the way, do you know why I'm so confident that deep learning is ruling the roost of the day, but other learning algorithms will be equally useful. Do you know why I'm so confident? Because I have the crystal ball? You don't believe me, huh? But then how can I be so confident? You're so quiet. I hope they will provide the coffee. So then at least you can, vodka, right? Okay, in machine learning, there is a theorem. It is called, this guy is so quiet, he's talking about it. It's called the no free lunch. You said that my mom told me this. But hey, we do have this no free lunch theorem. That's why I'm so confident that many learning algorithms will be useful, okay? So, and that's why I'm also so confident that feature selection can help you. The problem, because we really face, is not we have too much data. We need more data. That's the message. We really need more data. Okay, now feature selection. You're convinced, right? Feature selection is useful even under the deep learning, this overwhelming atmosphere. Feature selection is still useful, okay? And then we have to look beyond just the deep learning in order to face all kinds of challenges. And so now, feature selection. In machine learning, there are two fundamental categorizations. One is called supervised learning, one is called unsupervised learning, okay? So with labels, then we call it supervised. Without label, it's unsupervised. But when you have some labels, very few labels, then it's called the semi-supervised, okay? So we can categorize feature selection in this way, but we can also characterize feature selection in terms of how are we going to select features, okay? So we have wrapper methods, filter methods, embedded methods. Of course, we just give you the fundamental categorization, and then you will be able to find all the variants later on. Supervised feature selection. I have to blame our Jundong. Because he didn't take my version. In the morning, I tried to make it larger, this one, okay? But good news is he already uploaded the same set of slides. It's a bit small, but usually my contribution is just to make font larger and picture bigger or something like this. But I want to tell you this. Label information here, feature information, then we have the training set, we have tester set, okay? We have tester set. Then we have feature selection, selected the features, then supervised the learning algorithms. And then we have a classifier here. But usually, basically, this is like for supervised, we have label. So after we select the features, we make sure that these features are good. You see, there's a loop, okay? This is not necessarily supervised learning algorithms, but just the criteria you want to measure your performance. Then you just do this selected features and apply the classifier. You try to see the performance. This is, again, very small, but it's unsupervised. Now it's more difficult because I don't even have label information. How do I know I'm doing well, right? There are several ways we are going to talk about it, but mainly we will use clustering performance. Clustering performance. Okay, one thing you can rest assured is this. In data mining and machine learning, we always separate training data from tester data. So we don't cheat, okay? In the old days, like when I was a student, you only need to do what? Like you separate data into training and test and run the result and you publish papers. But now, nobody would accept this, okay? So then semi-supervised learning, then the key here is a partial label. But then there are many different ways to perform semi-supervised learning, okay? One way, for example, you can propagate the label, right? The labels, the instances with labels, and you find ways to propagate the labels to the others. Another way is you specify certain constraints and then make sure that these constraints are consistent with your labels. But there are many methods, okay? Now, we will categorize feature selection methods using how we, based on the strategies we select features. So one is called a wrapper model. Of course, you can read the slides, but a wrapper model is very simple. You say, I want to select the features for this particular application, basically. Okay? So I already decided which learning algorithm I'm going to use, so I just use it for feature selection and for learning. You say that. How can you do that? Will that work? Yeah, amazingly, it works. You see? Okay, so this is the wrapper model. We also have a nice figure here. The wrapper is you include the learning algorithm in the evaluation of feature selection process. So it's very simple. We also have a filter model. You say, hey, then you select the features that are too specific for that learning algorithm. What if I want more general features, right? So then you use filter model. You ignore the learning algorithm. You just try to use some criteria. Say what are good features, okay? Again, later on, I think Jiliang will talk about these methods. Do you see the difference? One is you use learning algorithms, so this one is you don't. Then we have a lot of smart people in feature selection. Then they just say, hey, how about I integrate both? So basically, you integrate feature selection into learning algorithms. Have you heard about ID3? Some of you. But if I tell you this is basically C4.5, it's even more difficult to understand. If you're from Europe, probably you know C4.5, huh? Or from Australia, okay? But if I tell you decision tree, then everybody knows. But ID3, basically it's a Ross Quinlan's invention of induction of decision tree. Okay, Ross Quinlan is Australian. Okay, so you select features, then you try to learn the tree and learn the decision tree. Then after you learn the decision tree, you also have a learning model. Okay, that's why this model is very good. You have a tree. What's the advantage of having a tree? Because you know what's going on. You know how a decision is made by tracing the path of the tree. Challenges in the era of big data. Conventional feature selection algorithms are naturally designed for conventional data. And the recent popularity of big data presents new challenges to conventional feature selection. So that's why Jundong, when he started this, we have a very, very long survey. You think 160 slides is long, but we have like 60 pages of survey. Jundong, I spend day and nights on this, and it's available online. And because of the new data types, data variety, data velocity, and data volume. We only include the 3 V's, but you can add a lot of V's. It doesn't matter. But basically, the key is we have new data types, and we have new challenges. So this tutorial is called From a Data Perspective, okay? Now, this is sort of like a very, very clear how long is this tutorial will be, okay? It's hopeless, huh? You will stay here until tomorrow, probably. Okay, so this is the data, static and streaming. Then we go down. We have conventional data, heterogeneous data. Then for conventional data, we have flat features, structured features. For the heterogeneous data, we have linked data, multi-source data, multi-view data. You see, we have so many of these different data types. And of course, again, remember, no free lunch theorem, and there is no universal feature selection algorithm either, okay? So I think that's my introduction part, and Jiliang will talk about the rest, the conventional part.